want this again. Hey, Tiara. I see you now. You see me? You hear me?
Mm-hmm.
You doing okay today? Been outside lately?
Mm-mm.
Okay. You get some fresh air. You feel okay about the test? Yay, no.
I tried.
Okay. I think I feel pretty good. You never feel good about anything about the test.
Exactly.
I know. So I don't even. I'll look at it and I'll tell you how you ought to feel about it. Okay. Have a feeling it'll be all right. So, your family okay? Like, who knows? Okay, let's see what we got here. It's just me and you right now. How your other courses going?
I still got 2 more tests to go.
When is that? Is that this week? The end of this week?
It's this week.
Okay. So is it tomorrow? Because we don't have
I,
classes Friday, right?
yeah, one of them got extended until Friday because she forgot to upload something.
Okay. All
And
right.
then, so I just have genetics and chemistry left. I finished Shores and I finished psychology.
Okay. Good. It's a big week. I think everybody wanted to get a test in to, I don't know, to get something going here. I don't know what it
I
was.
guess. I don't know what they're doing, but
Yeah.
oh well.
Well, it'll be a little while before we have another one. So we won't worry about that for a while now. So we'll just be doing little quizzes from now on.
I'm
Well,
just
from now
trying to
on.
survive.
Yeah. I know the feeling. Trust me, I know the feeling. All right, I just let Deanna in, I think. Let's see where she is. Yep, she's down there somewhere in the ether. Yep, I see her with her poster behind her. How you doing, Dion?
Good.
Okay, good. Family okay?
Mm-hmm.
You get outside and get some fresh air?
Yeah.
Anywhere to shoot some baskets?
Right outside.
All right, good. That's a good release. I used to do that when I was doing that kind of stuff. My basketball career ended when I was in a car accident, and I messed up my hand, and it messed up my elbow. And every time I tried to take a shot, my elbow would just catch, and I was like, "Oh well, can't do this anymore." So I just have to satisfy myself by watching. Okay. I think I just let somebody else in. Wonder who it was. That's Deborah, I bet. Okay. Guys, I'm going to go ahead and share the screen and we'll see where we are. Let's do that. We'll do that while we're waiting. Oh, there we go. There we go. So, okay, let's see. That might be my last person to let in. Alexis. Okay. Good. I think I got everybody now. Okay. So guys, I don't expect you to have worked on this homework because I know you were busy working on your test. And I know everybody's got lots of tests at the end of this week. So I need to add a little more to this, not a whole lot. It's two different sections, but it's not a whole lot of stuff to do. So after you finish your test this week, try to work on this a little over the weekend. There's no quizzes due or anything, so we don't have to worry about that yet. So, and I'm pretty sure that the online assignment sheet was a little bit off because we hadn't decided when to have the test then, but you'll see what we're doing. What we did last time was 10.3, and what we're doing this time is 10.4, but just to get you kind of back in the swing of things, I'm going to go through a little bit of this 10.3 again. So when you look at the homework, it won't be like you did it 10 years ago. All right, let me see what I got here. All right, I see Deborah's D. I see Alexis going out the door somewhere. I don't know where she's going. There's Dion, and I got Tierra. Okay, Alexis will be back in a minute, I hope. Okay, so guys, what we were talking about when we last met was these things called improper integrals. Okay, so I think the video, I'm not sure the video of this posted well. I had a couple that didn't post well one day. So I'm just going to kind of run over this, and you'll see it again probably in this, well, definitely in this video. So what we're doing here is what we're doing today, what we did the other day and what we're doing right now are called improper integrals. Okay, so improper integrals. Okay, the thing that made this first type we did improper was that that they had a limit on them of infinity. Okay, so if I go up a little ways, I look at this. We were looking at things that look like the limit or the integral from a to infinity. So the question was, what do we do with infinity? And the answer was, what we do is we replace that with just some t. And what it kind of looked like was that we were just letting t go further and further out the line, whether to the right or to the left. We replaced it with t, and then we took the limit as t goes to infinity. You are never going to be plugging in infinity. You're going to be taking a limit as t goes to infinity, all right? So you always need to do this first step here. So that's what these look like. You could go from a to infinity, which means you were going from a point out to the right indefinitely, or you could go from minus infinity and come from the left and go up to a. Our terminology was this. If that limit existed, the improper integral was said to converge. If it did not exist, the improper integral diverged. Everybody see this is a little bit narrow here. I did an example. I'll just go through this particular one right here. I did an example that said, okay, let's set this integral up here. It's an improper, boy, I scribbled all over that page, but it's an improper integral because of that infinity. I replace it with t and let t go to infinity. I integrate like I normally would. I plug in the limits. And once I get the limits plugged in, I let, this should be a t, guys, not an x here. That's my bad. So that's a t. I'm so used to writing x going to infinity, but it's a t that's going to infinity. All right. Clearly this piece of it right here, the denominator is getting bigger and bigger, so it's going to 0. Plugged in the lower limit, I just got minus a minus 1, minus a minus 1 over 2 minus 1, which was 1. And so we say it converges to 1. Converges and the limit's 1, or whatever, however you want to say that. Okay, so that's essentially what we were doing. And then we could do it from either side. In this one, we looked at minus infinity to 1. So it looked like the limit as t goes to minus infinity of the integral from t to 1. We integrated it. We plugged in the limits. We tried to see what's happening. What I want you to see on one like this one, if t is going to minus infinity, that is becoming a bigger and bigger negative number. And if that becomes a bigger and bigger negative number, we write it without the negative power, would be down in the denominator. So the denominator is getting bigger and bigger. That's why it's going to 0. Okay? So that was one thing we did. The last thing we did was, what if both limits are infinity, or one is minus infinity and the other is infinity? We talked a little bit about how it was sort of finding the area under a curve here. I had a really good problem that uses statistics to see some different things, but we don't have access to Maple, so that's one thing I've had to kind of let go. because it's something you can't integrate, and we were going to let Maple integrate for it. But the whole point here was that we could break it up at any point in between minus infinity and infinity. So a lot of times it's easy to break it at 0. And that's what I did in that one. That one ended up, that one will converge if both of them converge, if either one of them diverges. If you were to do this problem and you found out that diverged, you don't have to worry about that part right there. Because if that diverges, the whole thing's going to diverge. Okay, so they either both converge or the whole works diverges. Okay. So it doesn't matter what A is. I did that example. We looked at the inverse, what the inverse tangent looked like. I didn't look at this one, guys, but if you want to look at an applications problem on this thing, there's one on page 508, and it has to do with how much work is required when you're, say, launching a satellite or something out into space, and how much work it takes. So really what you look at, this problem, you can look at it, I'm not going to set the whole thing up, but it turns out that if it's launched from the surface of the Earth, the gravitational pull is really from the center of the Earth. And the center of the Earth is 4,000 miles deep, basically. So what you're saying is how much work is there added up. Remember, work was force times distance added up with an integral. You're looking at how much work it takes to pull it away from the center of gravity, 4,000 feet below, up into infinity. And infinity essentially is to go into space, how far you have to go into space. So that's kind of an interesting problem if you want to look at that. The homework was this stuff right here. There was something in the homework that I want you to look at. It's a comparison test, and it talks a little, I didn't talk too much about that the other day, but it compares integrals. So if I had this, and I had this integral of 1 over x squared, which would be the smaller of those two things? Which fraction would be smaller, guys, if you went from 1 to infinity?
1 over x.
1 over the x squared, because the denominator is bigger, right? That would make the fraction smaller. So actually, that 1 over x is bigger than 1 over x squared. Now, what these comparisons tests say is, if this one diverges, if one that's less diverges, now I don't know whether that diverges or not, but if you've got something that's less and it diverges, something that's bigger than that also diverges. On the other hand, if you got something bigger than something less than something's bigger than converges, then it will converge. What I want you to do on those two, that was these two problems right here, is read what they say and see if you can figure out, without working the integral, if I said, okay, this one diverges, what will this one do? Well, because it's bigger, it will also diverge. It's just like you can't, if it doesn't reach a limit in its smaller form, it's not going to reach a limit in its larger form. Okay, so you can look at that and we'll talk about it later. All right, the next thing I want to do is the next section, which is kind of short, but it's another part of improper integrals, and that one is this section right here. So it's section 10.4. This will be the last thing we do in chapter 10. After we finish this, we're going to go to chapter 11, which is on something totally different. It's on sequences and series. So when I look at this, it says, what if we have an integral in which the integrand, and guys, that means the thing you're trying to integrate. The integrand is the thing you're trying to integrate. What if we have an integral in which that integrand is discontinuous at one of the limits of integration? So it's not that the limits are going to infinity, is that if you tried to plug it in, you get a problem. Okay, this thing is not defined at 3. So the question then is, what do you do with that? This is one like that too. What happens if you try to take an integral from 0 to 1 and the function isn't even defined at 0? As a matter of fact, in that function right there, what you would have is an asymptote there. This one's a little different, but this one would definitely have an asymptote there. Okay, so whereas the last section was improper because it had an infinity and a minus infinity in it, in the limits, this one is improper because one of the limits makes the function undefined, or it's discontinuous there. The word's pretty easy, but let's take a look. So in general, what we'd be looking at is something like this. Suppose we wanted to take an integral. Oops, let's don't do that yet. Let's do this. Suppose we wanted to take an integral from A to B, this one right here. And at B, there happened to be an asymptote. Now again, if you want to think about this as an application, what we're trying to do is see if we can find out what the area under there is. But what you see is that as you go to B over here, and you want to stay within this region, so as you go to B, we got a problem with the function. We got an asymptote. So we're going to define it like this. We're going to say, if we're in between A and B is our upper limit, we're going to look at a limit as t goes to B from the left. That one right there. If the upper limit is the problem, you got to stay in the interval from A to B because that's what your integral does, and you're coming into B from the left. And then we're going to do the same thing we did a minute ago, well, in the last section. We're going to replace the problem with just a t, so that we're kind of letting t get closer and closer to B. And it's got to be from the left. It's got to be from the left if that upper limit is the problem. So let's look at an example of that. Has anybody got any questions right now? Comments? You okay? Okay, so here's what I want to do. I want to look at this one right here. Let's move it down a little way. Let's see what we had to do. This one was the integral from 0 to 3 of 1 over the square root of 3 minus x. The problem with this is that 3 right there makes that denominator undefined. If you tried to take an integral and plug it in, you might get a problem trying to plug in 3. But so what we're going to do, you're approaching 3. You got it because you're in between 0 and 3. That's what your limits tell you. You're going to approach this from the left. We'll see later it's different if you're looking at the lower limit. So I'm going to take the limit as t approaches 3 from the left of the integral from 0 to t of this thing right here. 3 minus x to the minus 1/2. And you guys are all experts at integrating now. So what we're going to do is integrate this, not too hard. U is 3 minus x, and U is 3 minus x, du is minus dx. So I get a minus. This thing with the power will be 1/2 over 1/2. Now let me tell you something. You cannot leave this in terms of u. You always have to go back to x because these limits are x limits, and I really don't want to change them. So you want to always go back to x before you start this process. Okay, something's getting a little bit, no, it's not cut off for you guys, cut off for me. Okay, so so what we do when we integrate it, we just simplify it a little bit. Simplify this thing right here, and right there. Invert and multiply, we'll get the minus 2, and it's 3 minus x to the 1/2. I then do what I always do. I plug in the upper limit. So I plugged in a t, which was the upper limit right there. First was minus 2, 3 minus t to the 1/2. And then I plug in the lower limit, 0, and we get that one. Now we take the limit. Once you get it integrated, you plug in the limits, you take the limit. And in this case, 3 is coming from the left. Now, it's important that it's coming from the left here because that means 3 is a little bit less than, it's a little bit less than 3 when I'm coming from the left. So you see right here, I'd be coming through values that were a little bit less than 3. That's important because I want to take the square root of them, and I wouldn't want to take the square root of a negative number. So, but as I get closer and closer to 3, that limit, 3 minus 3, that's 0. You're just getting closer and closer. If you're subtracting something closer and closer to 3 on the left from 3, you're going to 0. It's just like plugging in the 3, just to make sure that things are okay in terms of being under a root here. The last one, all I have to do is plug in the lower limit. When I plugged in the lower limit here, let's see, that first one went to 0. Right there. When I plugged in the lower limit, I got minus a minus, which is plus 2. 3 minus 0 to the 1/2 is root 3. I get 2 root 3. That thing converges to 2 root 3. So that's an example of what happens when you got a bad, you basically got a bad limit, and it's not in infinity or minus infinity. Okay, let's look at another one. Questions about that one before I move it up? Okay, so let's look at this one. This one says the integral from 0 to 1 of 1 over x. What's the problem point in this one, guys? What's the problem point in this one? Anybody?
0.
0. Now this time the lower limit is the problem. So if you look at this one, 0, there is an asymptote right there. So that's the problem. And the graph, of course, is shooting up, getting closer and closer to that. We're trying to see if there's can be a number assigned that would be, maybe would mean the area here. Notice that because you have to stay in between 0 and 1, because that's what your limits are right here, you will have to approach the problem point from the right. So always stay in your interval. Approach the thing by staying in your interval. So the way I'm going to rewrite this is the limit as t approaches 0 from the right. I'm going to replace the 0 with the t, and then I'm going to go from t to 1. I do what I always do. I take the integral, which we know is log x. I'm still taking the limit as t approaches 0, but I'm not going to take the limit until I plug in the limits. When I plug in the limits here, right there, I get log of 1 is the upper limit, so that's 0. Oops, that's 0. Log t minus the lower limit is minus log t. Now I'm approaching 0 from the right. Always, this is one you got to put in your pocket, guys. The log of t looks like this. And I didn't leave a lot of space down there, but if you go to infinity, it's going to infinity. It's getting bigger and bigger. But if you go towards 0 from the right, what's happening to it, guys?
Negative infinity.
Yeah, it's going to negative infinity. So what we would have here is negative, there's a negative already there. And since it's going to negative infinity, this thing is going to infinity. And because that limit is, in other words, the limit does not exist, we say this thing diverges. Okay, it diverges. So if the limit exists and it's some number, it converges. If the limit doesn't exist, if it goes to infinity or minus infinity, it diverges. So I think when you start to do some of these things, you'll see that maybe some of the problems you might have. I don't know. The integration shouldn't be a problem. Sometimes taking the limits a little bit dicey because there's some functions you might not know what they look like. You can use your calculator to see what they look like, see what's happening. One other thing you could have here is this. Look at this one right here. And this is easy to miss, guys. This one right here is the one I want to look at. And you could potentially do this. You could say, I'm going to take the integral of that. I'll plug in 4. I'll plug in 0. I won't have a problem. But you do have a problem because there's a problem in between 0 and 4. What's the problem in between 0 and 4, guys?
3.
3. Okay. This is a problem. If you've got a problem with the function in the middle of your interval, you're going to have to break it up. You're going to have to split it into 2 parts. So in this one, we would look, say, right here from 0, and we would go over here maybe to 4. So we're going to have to look in this part, and we're going to have to look in the other part. And the other part might be that. So essentially, guys, we're gonna have to set up two different integrals, two different limits here. And if both of them converge, then the whole thing converges. If they don't converge, then it diverges. If either one of them diverges, the rest of it's going to diverge. Let's talk about how we would set both of them up. All right, so I wish I had the picture in the, I'll tell you what, I'm going to do it over here and then I'll show you what I did there. On this one, if I took it as two pieces, I'd be looking at the integral from 0 to 3 of this thing. And if I looked at that one, I'd be looking at the integral from 3 to 4. Okay, that's squared. Dx. And see, what I've got is 2 now. This one has a bad upper limit. This one has a bad lower limit. So I'm going to set this one up as the limit as t approaches the 3 is the upper limit's bad. So I'm in between 0 and 3. I'm going to have to approach 3 from the left. Approach 3 from the left. I need to stay in that interval. And then the integrand is the same. It's the integral of 1 over x minus 3 squared dx. This one, the bad spot is 3 and it's at the bottom. So what I'm going to do in that one is I'm going to have to approach 3. So that's going to be the limit as t approaches 3. But in this case, it's going to be from the right. I have to stay in between 0 and 4 of the integral from t to 4 of 1 over x minus 3 squared dx. Okay, so you're looking at 2. You just set 2 of them up. So let me show you what I wrote down here, which is the same thing I had there. So that means the integral from 0 to 4 is the integral from 0 to 3 plus 3 to 4. If either diverges, then the whole thing diverges. If both of them converge, then it converges. So there's how I set it up. 3 from the left at that upper limit there, from the left-hand side. If it's the lower limit, I have to be between that number and 4, so it's got to come in from the right. All right, let's work it. Let's see what we can do with it. All right, any questions about how I set it up? I tell you what, before I work it, I'm going to go, because I know I'm going to have to integrate this thing again. I'm just going to go down here, and this is what I kind of like to do when I'm working these things. I kind of like to go down and integrate it so I'll have it ready to plug the limits into, guys. So I'm just going to integrate x minus 3 to the minus 2 dx. Whoa, what happened? Let me go back. Okay, down here. And so tell me what that integral is going to be, guys. Oops, I don't want to do that. You can tell me what that integral is going to be without me doing much. What's it going to be equal to?
Negative 1 over x minus 3.
Okay, negative 1 over x minus 3. Because as you can see, you just use the power rule on it, and if you let u be x minus 3, du's dx, so you don't have to really do anything. It'll be x minus 3 to the minus 1 over minus 1. There's the minus 1 dropped it down here, and that's what I got. So let's go back up here and finish this one out. So I'm going to end up with the limit as t approaches 3 from the left of the, I already integrated it, so minus 1 over x minus 3. I'm going to plug in 0 and t. Those are my limits. This one, with the limit as t approaches 3 from the right. And that's going to be, again, minus 1 over x minus 3. Good thing about splitting it up is you just have to integrate it once. And that's going to go from t to 4. Now, you can always tell you got everything right here, guys, because you're starting at 0, you're going through t, Remember that from Calc 1 where you went up and down and like that? You're going from 0 to 4. Okay. All right, now I got to plug my limits in. The limit as t approaches 3 from the left of -1 over t minus 3. Minus a minus is going to be plus there on that limit. And if I plug in 0, I'll get 1 over -3. All right, what I did there, guys, I knew there was a minus on this, so I was subtracting the lower limit, so minus a minus, and then I plugged in the 0 here, and I got 1 over -3. So I'll look at that one in a minute. Plus the limit as t approaches 3 from the right of plug in the upper limit, I'll get -1 over 4 minus 3. Minus a minus again is plus 1 over t minus 3. Okay. Now we gotta just take the limit and we'll be able to decide what we got here. What you're really doing, guys, is looking at a function that looks like this now. And you know that that function has an undefined spot at 3. And you also know there's an asymptote there. So if I were to think about what the thing that I integrated looks like, I'd be looking at something like this, which had a discontinuity at 3. That's not the original function, but the one you're trying to decide about the limit. So if you approach that from the right, the graph I think looks like this. So if you approach that from the right, this one's going to do the following. That'll be -1 plus. If I get closer and closer to 3, guys, what is this one doing as I get closer and closer to 3? Look at the graph. It's going down, isn't it? Yeah, it's going down. I mean, you're dividing by a smaller and smaller number. If I get closer and closer to 3 from the right, like 3.1, difference would be a 10th. 3.2, difference would be 100th. You invert and multiply, you're getting bigger and bigger numbers. So that's going to infinity. Now, I don't care if I add -1 to infinity. Guess what? I still got infinity. It's that one right there. That side's going to infinity. Now, I want to play this out because I want to show you the limit again. But now that I know that one of them diverges, the whole thing has to diverge. Okay? Because both of them have to converge to converge. But if I look at this one, again, it's the same graph. It's -1 over t minus 3. That makes it a little different. It's still got an asymptote at 3, but the graph ends up looking like that. Okay? So as I approach t from the left on this, because it flipped it basically because it had that minus sign up there. As I approach t from the left, I'm going to infinity. So this one looks like infinity, and the limit of -1/3 is -1/3, but guess what? Take a drop out of the ocean, still got a lot of ocean, okay? It's infinity minus 1/3. This one diverges too. Both of them diverged. So what we say is that this one diverges. Again, if you had found out that either one of them diverged, you could, based on our theorem, you could say that the whole thing diverged. Does everybody see how I split it up? About the limits? All right, I'm gonna do one more, then we're gonna call it a day, okay? Oh, let's look at this one. Where do I need to split this one, guys? Where do I need to split this one? What's the problem?
At 1.
Be careful, it didn't 1, it's what?
-1.
At -1, yeah, at -1. Now, really, guys, if you were to see this on a final exam and you were just doing integrals all along, you might just take the integral without thinking about it and plug in the upper limit and plug in the lower limit, and you're going to get an answer, but it won't be right because you kind of just skipped merrily over that discontinuity and it was an improper integral and you didn't recognize that. So from now on, when you're integrating things with limits, make sure that the function is defined everywhere in between your limits. So we got -1 is the issue here. So let's see. I'm going to split this at -1 then. I'm going to go -2 to minus 1, and I'm going to rewrite this. It's just going to be x plus 1 to the minus 2/3. Okay, dx. I'm going to split this one, and it'll go from minus 1 to 7. So I take up the whole integral, and that'll be x plus 1 to the minus 2/3 dx. Okay. Okay, so we've got one problem at an upper limit and one problem at a lower limit. What it's going to look like. Since I'm in this one right here, I'm in between minus 2 and minus 1. I'm going to need to approach minus 1, since I like to do it like this, guys. If this is minus 2 and this is minus 1, and I got to stay in there, I know I've got to approach it from the left. Okay, so the limit as t approaches minus 1 from the left of, hey, let's go ahead and integrate this one, guys. Tell me what the integral of x plus 1 to the minus 2/3 will be. Let's do it down here. X plus 1 to the minus 2/3. What's it going to be? Anybody?
3x plus 1 to the 1/3.
Yeah, because u is x plus 1, d is dx. I don't have to change it. If I add 1, I get minus 2/3 plus 1, which is 1/3, and divide by 1/3, that gives me a 3. So it's 3x plus 1 to the 1/3. Otherwise known as, and this might help me a little later on, the cube root of x plus 1. So there it is integrated. I don't have to worry about it anymore. Everybody see, I'm going ahead and doing that. So this is going to be the limit as t approaches minus 1 from the left of this 3 cube root of x plus 1, t plus, yeah, okay, of x plus 1. Should be a t, hang on one second. Get my notation look. This is a, t is approaching minus 1. Yeah, that's fine. I hadn't plugged in the limits yet. That's why I don't have t's there yet. I got myself confused for a second. Okay, that's 1. And then I'm going from minus 2 to minus 1. Let's get away from that. This one will be the integral or limit as t approaches. Now, if I got to stay between minus 1 and 7, I'm going to approach minus 1 from the left, from the right, sorry. Minus 1 from the right. And it'll be the same thing, 3 cube root of x plus 1.
So why didn't we put t's in it this time? Like
We are. That's what I got myself a little confused on. This one's going to go from minus 1 to 7. So what's going to happen is we do need t's. So when we rewrite it, it's going to be, you know, I skipped a whole step. No wonder I'm messing myself up. Let me just hang on. Let me do this again. We know we've got everything done there. Let me show you what I should have put in there. That I was confusing myself by leaving out a step. Take that lesson. Okay, that was my problem. So here's what it would look like. Here's how the t's go in first. The first one's going to be the limit as t goes to minus 1 from the left of this integral, which was, we already integrated it. But we would say what it would look like then would be from minus 2 to t of whatever the thing was. And it was x plus 1 to the minus 2/3. I left out a whole step out. Dx. Plus the limit as t approaches minus 1. This one is going to have, since we need to be between minus 1 and 7. I hope everybody's seeing what I'm doing here. If I'm going to be between minus 1 and 7, we got to approach minus 1 from the right. And then we replace the minus 1 with a t there. So t to 7 of x plus 1 to the minus 2/3. Sorry, I'm getting a little messy here. That's the whole, I skipped a whole step. That's bad. Okay, so now let's finish it up. This is going to be limit as t approaches minus 1 from the left of this thing integrated, which we said was 3 times the cube root of x plus 1, evaluated from minus 2 to t. That's how I'm going to get the t in it. I don't know what I was thinking. The next one will be limit as t approaches minus 1 from the right of 3 cube root of x plus 1. But that one's going to be from t to 7. So change it to, split it up, change it to the limit form, replace your bad spot with a t, and let t approach that spot. Okay? Now let's take the limit. Now I get the t's plugged in, guys. Let's do that. When I plug the t's in, so we're going to approach minus 1 from the left. This will be 3 times the cube root of t minus 1 minus the lower limit plugged in, which will be 3 cube root of minus 2 plus 1. So that's what that one looked like. And I'll take the limit in a minute. Plus, I'll do the next one under it. The next one's going to look like the limit as t approaches minus 1 from the right. I'm going to plug the upper limit of 7 into that. So this is a cube root of 7 plus 1 minus the lower limit plugged in, which is cube root of t plus 1. Okay, so together, those are those two things I have to find the limit of. All right, let's look at it. As we approach minus 1 here, the t's getting closer and closer to, that's a plus. Sorry, that's a plus right there. See, that's it didn't show up with my pen. If I approach minus 1, what's going to be under this radical here? If I'm getting closer and closer to minus 1 and I add 1, what's this getting closer and closer to?
0.
0. Good. It's getting closer to 0. This one's gone. On this side, I've just got a constant left. And if you look at it, that's the cube root of minus 1 right there. Add the minus 2 to the 1. Cube root of minus 1 is minus 1. Minus 3 times minus 1 will be a positive 3. So this piece goes to 3. So I'm still in the game here. If the other one exists, then the whole thing's going to exist. When I look at this one, this first thing right here, that's the cube root of 8, which we know is 2. So that's 6. Now, if t approaches minus 1, and you add 1 to it, what's that thing doing?
0.
0. Yep, that one's gone. 3 plus 6 is 9. It converges to 9. Okay? Are you okay with that? Guys, I don't know if, the last time I tried to put a video, one day I had, when's the last day I taught you guys anything? Monday, I think. The video didn't work. I didn't know why. It messed up in both my 11 o'clock and my 1 o'clock class. So that's why I kind of went over it, and I never posted it. I posted it and it lasted 5 seconds, okay? So if that happens, if it's still up there and it's only got 5 seconds in it, that's why I went over the first part of this. So in this lecture right here, you've got all the different kinds of improper integrals. This next homework is on this particular kind. So there's another thing that has to do with what's called a comparison test. We can talk about that later if we need to. But the rest of these are problems that have bad spots in the limits, but in between the two limits. Okay. Got any questions? Anybody got any questions?
When is the quiz due?
Oh, don't worry about that. Let's say we meet again tomorrow. We don't have class Friday. So I'm not going to put that quiz due until Monday, okay? Because you hadn't had a chance to do the homework on that 10 point, whatever it is. And I think that first one, I'll look at the quiz again. I don't know if it has both kinds of the different improper integrals on it, but I'll look at it again. But the earliest it's going to be due is Monday. So you have time to ask me questions about the homework tomorrow.
Alright.
That sound okay?
Hmm.
All right. Anybody else? Question? All right, I'm doing something I don't do very often. I'm letting you go because I know you got lots to do. And we're all
Tiara
tired.
has a question.
Yeah, what? Who had, Lexus got a question?
No, Tiara.
Tiara got a question. Where's Tiara? Where are you? Tiara, what's your question? I don't see her. I think she left.
Oh, I think she was saying bye. Never mind.
Oh, okay. It's like, okay.
I
Anybody
thought
else?
she was like,
Either say bye or ask me a question. Everybody okay?
yeah.
All right. I'll see you tomorrow, okay? All
See you
right.
tomorrow.
Bye.
Bye.